So up here we talked about matter can either be a pure substance or a mixture. If it's a pure substance, it can either be an element or a compound. Of course, those are related by chemical reactions. You can take elements and make up to compounds, or compounds break down to its elements. So two types of compounds we talked on Monday when we met. The two types of compounds were molecular compounds and ionic compounds. I'm like pointing up here like they're still up here. Actually, I think I took a screenshot of that and posted it out on Twitter just because I could. So in tomorrow's lab, we're going to focus on ionic compounds. So I'm hoping to kind of get a little bit of that background out today. So of course, ionic compounds involve ions, okay? Ionic compounds involve ions. And we have been talking yesterday how I put an M, the letter M stands for metals. Metals tend to form cations, positively charged by losing electrons. And that's what's being shown here. The jag represents the jag between metals and nonmetals. It's like a battle between metals and nonmetals. And then you see actually how aluminum, if we find aluminum on the periodic table, aluminum, it is right here, and it's going to lose 1, 2, 3 electrons, and then it's going to have the same electron configuration as the rare gas in the period before it. So that's why aluminum is going to neon, okay? Rubidium, where's rubidium going? Well, rubidium's right down here. It's going to kick off 1 electron. It's have 37 protons, now have 36 electrons, and it will be like krypton in the period before it. So that's how that works. So metals tend to kick off electrons and form positively charged cations. Nonmetals tend to pick up electrons and form negatively charged anions. Cation, anion, metal, nonmetal. And I think I'm a fan of nonmetals because I just think it's neat, for instance, how neon is 5A. One of these days I'm going to take a marker, but 5, 1, 2, 3, 4, 5, 6, 7, 8. 5A, it has 5 valence electrons. It needs to pick up 3 electrons to be like neon. Okay, so nitrogen picks up 3 electrons to be like neon, oxygen picks up 2 electrons to be like neon, fluorine picks up 1 electron to be like neon. And all the way, they're forming a -3, a -2, and a -1 charge when they do that. Okay, so we have metals and nonmetals, cations and anions. Tomorrow we'll be talking about ionic compounds. And then the next Thursday, we're going to be talking about what's called Lewis structures. Actually, next Thursday we'll be eating turkey. The Thursday after Thanksgiving, we'll be doing Lewis structures. So these aren't Lewis structures, but in the back of your mind, we'll be talking more about Lewis structures. These are called just simple electron dot formulas for the elements. So if you look at each of those dots represents one of those fancy valence electrons around an atom of that element. So for instance, if we pick on nitrogen, nitrogen's 5A, it has 5 valence electrons. You see 5 cute little dots around there. Okay, neon is 8A. All of the rare gases have 8 valence electrons. You see 8 electrons around there. So that's kind of how that works. Helium, okay. Helium is atomic number 2. It actually is a rare gas, even though it doesn't have a complete octet. It's full with, remember, the first stop is the 1s subshell, and it completely fills it, 1s2. That's what helium looks like. So it's also got a rare gas configuration. Okay, so now I just have some pictures to kind of show you what this looks like. If we think of it as like a chemical reaction, where you have reactants going to form products, and then over the reaction arrow, I have what's being, in this case, subtracted. So subtract 1 electron from a sodium atom. Subtract 1 electron. Sodium its neutral has 11 electrons. Okay, if you take off 1 electron, it's going to have 10 electrons, and it's going to have the electron configuration of neon. So it's going to look like this. Where now, if I were to draw the electron configuration of neon, any of those rare gases, they're 8A, so they have 8 valence electrons, and here we go, 2, 4, 6, 8. Notice that I'm showing that this is the sodium cation. I put it in brackets and I put the charge outside. The reason it's +1 is because now it has one extra proton in its nucleus than it does electrons, because it kicked one off because it wanted to be like neon. So if we pick on an example of a nonmetal picking up electrons, you kind of see reactants, going to form products. Over the reaction arrow, what's the difference adding one electron? So fluorine is 7A. You would see its electron dot structure like this, 7 electrons, 2, 4, 6, 7. And then it picks up 1 electrons, 2, 4, 6, 8 in brackets. Now it is negatively charged with a -1 charge. Sulfur is a 6A element, so you see 2, 4, 5, 6 electrons, and it is going to pick up 2 electrons, and in doing so, now it will be a -2 charge. Okay. So ions are things that where you have an unequal number of cations and anions. Each of the examples we've talked about are what we call mono, meaning one atomic atom. One atom ions. Okay, one atom ions. If it's positively charged, a cation, like what metals do, that means there's more protons than electrons. Must have kicked off an electron 2 or 3. Okay, if it's negatively charged, we call those anions. By the way, this is a favorite place to get vocab words for your next unit exam. There's all sorts of vocab words that you do. An anion is a negatively charged thing. It's a species. It's not an electron, not a negatively charged subatomic particle, but it's something that has now more electrons than protons. And why did it do it? Because it wanted to be like the rare gas in its period. So we've been talking about electron configurations. You know, that's how the electrons are hanging out. Okay. And we can now we're going to kind of segue into what happens if electrons come and go. How do those electrons configurations of cations look like? What do electron configurations of anions look like? Well, if we start with the metals, that are going to be losing electrons, the metals forming cations. And we're just going to focus on the 1A, 2A, and 3A. Remember, those are headers on your groups. The 1A, 2A, and 3A metals. Now, when we get to 3A, we have to kick boron out, don't we? Because it's a nonmetal. So starting with aluminum, gallium, indium, and thallium. Okay, so those metals tend to kick off electrons to get like the rare gas in front of it. So when we're going to look at some electron configurations of the neutral atom, and then we're going to see which electrons get kicked off. The electrons that are going to get kicked off are going to be in the valence shell. And hopefully you remember the valence shell is the highest N. Remember, once you see how the electrons are hanging out. And when they do that, lose their valence shell electron, then electrons, all of them, now their new valence shell is going to be N-1. I'll show you what that looks like. So in tomorrow, and actually a little bit today, I didn't bring it. I had my black and white periodic table out. What you're probably going to want to do, what a lot of times students do, is the top of this whole group, they write a +1 because they will form a +1 charge. So if you have like your, just flip it over, your periodic table, write +1 at the top here, because that's what charge they form. Because we're going to have some exercises coming up, and you're going to want to know that if you didn't already. So what do 2A form? What sort of ions do they form? A +2, exactly. So in the next column, put +2. And then 3A metals, after boron, form a +3. And I know I haven't chased it down, but I stopped with gallium, but I would add indium and thallium there too. Aluminum, gallium, indium, thallium. Oh my gosh, that rhymes. Okay, so they lose electrons. Let's see what that looks like. So, if you were going to write the electron configuration of sodium, it would look like this. Do you guys have this? It would look like 1s2, 2s2, 2b6. Okay. Oh, sorry. 1s2, 2s2, 2b6. Yep. And it peters out 3s1. Now, let's see, what's the highest N? 3. Very good. How many electrons are there in N is equal to 3? Just 1. Yep. So when I write Na +1, all I'm gonna do is write it minus the 3s1. Goes 1s2, 2s2, 2p6. Another one, aluminum 3A elements. It's gonna lose 3 valence electrons. And can you see what's the highest N here? It is also 3, yep. How many electrons we got? 3, yep. So they're actually all gonna go. When we write Al plus 3, this is what the electron configuration looks like. Okay. There's a word for it. I can't remember if I'm gonna bail on this to go to part 6 before I get there. But do you see how the sodium plus 1 and the aluminum plus 3, how would you compare their electron configurations? They're the same. There's a cool word for it called isoelectronic. They are totally the same. So let's look at aluminum plus 3. So what's the highest N here? Yep, it is 2. And do you see where this is? You told me this is 3, so 3 minus 1 is N minus 1, so this is 2. So that's how that works. With the ion, with the metal cation, the new valence shell is now going to be in N minus 1. All right. So do you remember, I'll write it over here, I know you do, but whether you'll tell me or not is another thing. So if I write the S-type subshell, P-type subshell, D-type subshell, F-type subshell, yep. What's the L value of S? It is 0. How about P? 1. Yep. So all this is saying is that if you have a choice, like with aluminum, you told me the highest N was 3. So beyond neon, it had the 3s2, 3p1, right? So the L value of S you told me is 0. The L value of P you told me was 1. All this is saying, if given a choice in the valence shell, it would lose electrons in the highest value of L first. So technically, if you had on a magnifying glass, you would see this one go first, and then this one. That's all that is. I don't know how you worry about such things, but actually we're going to talk on Friday about something called ionization energy. These 3 valence electrons are not created equally. Okay, this one will go first when you ionize it. Okay, so let's pick on iron. Very important in astronomy. The most complex atom that a star will make in its core before it blows up. We're just covering this, so that's fresh in my mind. So it's atomic number 26, so it has 26 protons, has 26 electrons if it's neutral. This is how the electrons are configured using the arrow diagram. Do you guys have this? Okay, I'll read it off. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. I would read this one out to you too. Now you won't have to do this on your test, but I'm going to unscramble them. So again, it's the 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. So 26 electrons are configured the same here. It's just to kind of highlight, so what's the highest N? It is 4, yep. So not so surprising, and actually one of the things we'll talk a little bit about today and tomorrow in lab is that iron has more than one cation it will form. So it definitely forms a +2 cation. And so the electron configuration is minus those 2 4s electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Again, if you were going to pair the neutral iron atom and the iron +2, the 2 electrons to go are in the valence. Okay. So I'm going to show you the Fe+3 now. So it's going to lose 1 more electron. First off, what's the highest N? It is 3. The highest N is 3. And so we said just a minute ago, now we have 3 subshells with N is equal to 3. So it's going to go from the highest L value. So where do you think it's going to lead from? Yep, 3D, going to kick off one electron. So for the Fe plus 3, it looks like this. 1s2, 2s2, 2p6, 3s2, 3p6, and now it's a 3d5 instead of 3d6. Which actually, we talked about this. Do you think, well, I'll answer my own question. Remember we said that actually electrons can appear to go up to a higher state if they get a nice, just a sweet half-filled D-type subshell? 5 is the magic number there. So that's kind of a fun place for iron to be. This is called iron having 2 oxidation states, or 2 different cationic forms. This actually is the problem we run into with, I'll just go ahead and, I'm a toucher sort of person. I'll go ahead, of course iron is here. I'm going to tell you 3 exceptions, but basically anything in here in the group B metals, just assume that they can do, again I'm going to show you 3 exceptions, just assume that they can have different cationic forms. Okay. So let's look at how the electron configuration changes when a nonmetal picks up electrons, and I'm sure this will make sense to you. For instance, So on the same place that you have the +1, +2, and +3, now if you would go find the 5A nonmetals and put a -3 at the top of that column. So beginning with nitrogen, that's a -3. Now, actually, I have nitrogen and phosphorus, arsenic, we talked about this. Arsenic actually, things along the jag, like arsenic, are metalloids. Okay, oxygen, sulfur, selenium, -2, fluorine, chlorine, bromine, and iodine, -1. So hopefully I'll label those. So let's see how the electron configuration of an anion looks compared to its parent atom. So chlorine is atomic number 17, 10 electrons around neon plus 7 electrons. So chlorine is 7A, and it's going to pick up 1 more electron. You can see how now we're going to call it the chlorine, I'll just call it the chlorine anion for now. What it looks like, it has the core of neon, so bracket Ne. Then beyond that, we have 3s2, 3p6. Of course, that 3s2, 3p6 is rare gas configuration. We'll do one more. If we pick on a neutral phosphorus atom, beyond neon, those 10 electrons, it has 5 electrons. So it's what, 15 electrons? So, I'm drawing a blank. So, in order to get what we call a complete octet, here it needs to pick up 3 more electrons here. So the phosphorus anion is phosphorus -3. Now it's beyond neon, 3s2, 3p6. Rare gas configuration. In the past, for the unit exam over this material, I have, I think this is right, I actually asked electron configurations of neutral atoms, and then I'll ask you electron configurations possibly of cations and anions. The good thing about today is I don't think we get to any homework slide. So let's see, this is Wednesday, so that means no homework due Friday. That give me time to do some homework. Okay. Yeah, so with all these electrons kind of coming and going, we end up with what are called isoelectronic things. I like the word species for things. You know, you have your neutral atoms, you have your cations, your anions, they are all species things. So for instance, you might recognize this 1s2, 2s2, 2p6, those 10 electrons are what we've been talking about, the core neon. So who wants to be like neon? Well, the nonmetals in the same period, right? And the metals in the period after it all want to be like neon. We have electrons coming and going. So all of these are isoelectronic, which means they have the same electron configuration. Nitrogen will pick up 3 electrons, oxygen picks up 2, fluorine picks up 1 to be like neon. Sodium in the period after it will kick off 1 electron. Magnesium kicks off 2 electrons, and aluminum kicks off 3 electrons. So they're all isoelectronic. So this is a good segue into compounds. So again, what are compounds? Well, you know what compounds are. They are, if you're going to talk about matter, matter can either be pure or mixture. If it's a pure, it's either an element or a compound. If it's compound, it's either molecular or ionic. So ionic compounds oftentimes are simply just binary, which means 2. So they have 2 types of elements that combine together to make that ionic compound. We've been talking about the metals will lose electrons, form cations. The nonmetals will gain electrons, form anions. That's just consistent with what we've been talking about. So one of the things, and we'll be hitting it hard in lab tomorrow, is that we need to be able to take any cation and any anion, put them together, and make what's called a neutral formula unit. I'll kind of show you what this looks like. I've got some more tips ordered for my stylus because I think I just was too hard on my other tips. So we'll see because my stylus is dead right now. So what's the formula for table salt? Yep, NaCl. That's the formula. So you can look at that sheets if you want, or look at the periodic table. Sodium, what sort of charge does it form? +1, perfect. Chlorine, +1. Chlorine, what sort of charge does it form? -1, perfect. So it's, in order to get if this is my cation and this is my anion and I want to make it neutral, I'm just going to confirm that I'm going to put an implied subscript of 1 here and 1 here. Does that sound okay to you guys? We have 1 sodium and 1 chlorine. It's implied if you don't have any subscript. Like H2O, we have 1 oxygen. So with that in mind, it goes something like this. We have 1 sodium. You guys told me it's a +1. And we have 1 chlorine. And you guys told me it's a -1. So what happens if you add all that together? What's that added together? What is it added together? 0. Yep. It's 0. So when we talk about a neutral formula, that's all we mean. Okay. I love ionic compounds because it's like you have 2 closets. You have a cation closet and you have an anion closet, and you get to pick what you want to make. So I'm getting a little ahead of myself, but I think that's okay. What if we go to our closet and we want to pick something from 2A. Let's pick Ca. So what sort of charge do we have for calcium? +2, 2+. Yeah, and I'm bad about +2 and 2+ are the same for me. I'm sorry. What if we're going to combine it with bromine? What's bromine? What charge is it for? -1 or 1-. Perfect. Do you see if I write the neutral formula as CaBr? Okay, I'm going to have 1 calcium. It's a +2 charge. And I'm going to have 1 bromine, and it's a -1 charge. Now, that's not neutral. So there must be something wrong here. Okay. It's called the crisscross method. So 1 and 1 doesn't work. And I'm a firm believer in the crisscross method. So what the crisscross method does is you go ahead and write the formula of your compound, but the subscripts work like this. So the subscript for the calcium is going to be the magnitude of the charge. So the subscript for the cation is going to be the magnitude of the charge for the anion. So we'll need 1 calcium. And then the number of anions you need is the magnitude of the charge on the cation. So we'll need 2 Br -1s. crisscross. So a few things though. Notice crisscross means it goes down. Sometimes students do this and they want to turn them into floaters. Okay, they are subscripts. And the other thing is I don't include the charge because this is a formula of a compound. So let's check, let's do the math. So I'm getting 1 calcium and it's a +2, and I'm getting 2 bromines and they are both a -1. Okay, so this is the neutral formula of that compound. So that's what this slide is talking about. A little bit about kind of taking this deviation from part, we're going to get there, but we're going to deviate here in a minute. Waiting to talk about sizes of cations and anions will help us tomorrow. So sodium, it will lose this electron, become a +1. Fluorine wants to pick up an electron, becomes a -1. And it's kind of like that video we watched, where an electron is transferred, electronegativity difference is great enough, and you end up with a -1 and a +1, and then the ... we have an ionic bond between those two. We see the Lewis dot structure of sulfur. Notice, actually, it looks like it's got homes for 2. It needs to pick up 2 electrons, form a -2 anion. These are going to kick off their electrons, which works out well. So kind of think of the electrons being kicked off of the sodiums are being taken up by the sulfurs. And then you end up with this S -2, but to balance it out, and you can convince yourself crisscrossing works here too, to balance it out, the formula is going to be Na2S. Okay? Here's where I kept thinking we were going to be. So fast forward, part 6. It should look something like this. Formulas and nomenclature. So nomenclature just means naming. So you're going to have to be able to crisscross, write the neutral formulas, and then I need to kind of talk you through some highlights of how do you name this. Now I warn you that this is the only place I can think of so far in this subject that you're going to actually have to memorize some things. So don't whine too much. I'll take a little bit of it, but not too much. We already ran into the term today, monoatomic ion. We've been talking about it, where one atom, a metal kicks off an electron of 2 or 3, becomes a cation, monoatomic ion. Non-metals pick up an electron 2 or 3 and become a negative charge anion. Well, there's these other types of ions called polyatomic ions, and you know them already. And you're gonna, if you don't know them, you will know them before, hopefully, you take the test. So if I write this up here, does anybody know what that is? First letter N. Ends in 8.
Nitrogen oxide.
Nitrogen oxide. That'd be a good guess. You're close. It's nitrate. Once I say it, you're like, I've heard of nitrate. Well, meat nitrate, exactly. That is nitrate. And so we have these 4 atoms, 1 nitrogen and 3 oxygens, those 4 atoms running around. And if you count up the protons, there's 1, let's see, less or more. There's 1 extra electron than there are protons in those 4 atoms. Okay, so it's a -1 charge. It's a polyatomic ion. Yep. So here's where we're going to go around the room. And since you're playing along with me at this end of the semester, I really like Canvas. I have a column now that says extra points, and I don't have to do anything for it. It asks me if you have any questions about it, but if I make it in Canvas where it's 0 points, and it's in the assignment set assignments, then any extra points I put in there go for your assignment points. It is a blast. So for just being here, I'm going to put 10 extra credit points in this. It's kind of like what you did the other day. So some of you, for your homework assignments, are going to be above 100%. Anyway, so we're going to start over here, Lindsay. So look at the periodic table and tell me what sort of ion that forms.
positive one.
It is a positive one. It is a positive one. And I run into this a lot. Sometimes we think it's a negative because an electron's leaving. I don't know. But anyway, it's a +1. One electron's kicked off. Okay, Sierra. -2.
Negative. I won't get BR.
So BR, yep.
-1.
-1, very good. And I'm awful with names. Gavin, Jared, is it Jared? No.
It's close.
Huh?
Me?
Yeah,
Oh, I'm Jacob.
Jacob. I thought it was a J. I'm sorry, Jacob. Okay, Jacob, very good. -1, perfect. Okay, Gavin,
+2.
+2, perfect. Tristan,
-3.
-3. Are they already written down for you?
No.
Okay, good. Okay, thank you. Write them down as you go. Okay, Lindsay, potassium, +1, very good. Sierra? -2, perfect. Next, Lori?
-1.
Jacob, -1. Calcium?
+2.
+2. And Tristan?
-3.
-3. Now, there are things you need to memorize, and I just covered this recently with my other class, my intro students, and sometimes students will think, oh my gosh, I have to memorize phosphorus? I have to memorize what charge that will form? And I'm like, no, you just look at the periodic table. It's okay, relax. Okay, so we okay with that? Okay, cool. So, the whole neutral thing, that's what this slide is talking about. This is the crisscross slide. So basically, when we grab our cation, and it's going to be in this order. We grab our cation, something's positively charged. We grab our anion, something's negatively charged. And we're going to make a neutral formula out of them. And if you want to, you can take your charges and crisscross, and then that's how many of the opposite charge that you need. Okay? That's it. But remember, the word here is subscripts. Remember to go all the way down with them. And don't include the charge. So, like I said, when you write, you guys told me the formula for sodium chloride was NaCl. It's not Na plus Cl minus. If you use that as your template, okay, you don't put the plus and the minus. Cations first, women first. Okay, anions last. When we talk about, when we go to our closet, this gets so exciting. But when we go to our closet, and usually it's the anion closet, and we pick something like nitrate, okay? And I'll just show you, and this isn't until the third set of tomorrow that we're gonna get to it. But let's just say, well, let's see. Let's say, well, I'll pick calcium. What if we wanna make calcium nitrate? And we're gonna crisscross. So you would hopefully tell me that I need 1 calcium, and I know you probably won't put that 1 there, okay? And I'm gonna need 2 nitrates. Does that make sense? What this rule is telling you, if I need 2 nitrates, that's why you'll see in chemical formulas like this. It's kind of like math. I have to put the NO3 in parentheses and then outside put the 2 to show I'm getting 2. If we do the math, I've got 1 calcium, it's a +2, and I've got 2 nitrates, and they are each a -1. I'm back to neutral. Okay, so that's how that works. What else we got? Oh, so we're going around the room. Who did we stop with last time? Do you remember? Tristan? Okay, so Lindsay? Okay, so crisscross, applesauce. It's just KCl. It is just KCl. And the sunshine band. Yep. Okay. Next, how would you crisscross, Jacob, to get the neutral formula here?
Al2 and S3.
Al2S3, perfect. Gavin?
FeBr3.
FeBr3, perfect. Tristan?
Ag2O.
Ag2O, perfect. Tomorrow's gonna be so easy. Look at it. Give me time to go do some homework. Okay, I'm throwing, back to you, Lindsay, I'm throwing a polyatomic ion at you. NH4 is kind of like NH4 plus 1 is kind of like NO3 minus 1. It's actually called ammonium. But if you're going to crisscross, what would that formula look like? NH4F, perfect. Again, now we've got, this one throws people off. It's actually not sulfate, which kind of rolls off the tip of our tongues. The fact that it has 3 oxygens like this, don't blame me, it's sulfite. So if you crisscross, now this one's a little tricky. If you crisscross, you probably get something that can be reduced. Remember we talked about, did we talk about empirical formulas in here yet? Okay. So, what do you think, Sierra? Yep, Cu1SO31, or just simply CuSO3. Why is that? Well, actually, one of the rules that I had a minute ago said you write the formula in the lowest form. So if we crisscrossed, we would get Cu2 quantity SO3 2 if we crisscrossed. But what we're supposed to do, and I go back and forth, sometimes like for my intro students, I'll let this ride. But for you guys, the real deal is that's the only pitfall in crisscrossing. Is if you can reduce these, then you need to. Very good. Okay, Jacob, what about the next one?
So Li2, then SO5. We're gonna add.
Almost. Li2, and you're just gonna bring this one down here, so it means you only need one of those groups. So it doesn't pick up an oxygen, it's just simply SO4.
Oh.
Yep. Very good. Li2SO4. Perfect. Okay, Gavin, what about the last one?
MgHCO3.
Yes. Mg and then quantity HCO3 subscript 2. Yep. Very good. Get 10 extra points. Come on, guys. Very good. So there's the crisscrossing that we did, kind of what I call the component cation and anion. The component ions you crisscross, you write the formula. That's perfect. The other leg of this is how do you name that compound that you've written? How do you name it? So that's called the nomenclature part. So the naming, you go ahead and you give it its first name, which is going to be its cation, and you give it its last name, which is going to be its anion. The cations look like the cations are going to be the metals, or the polyatomic cation, but the cation is generally going to be the metals. And let's see, for metals that commonly form one stable ion. Well, what metal did we just come across that forms more than one stable cation? Remember we did the electron configuration of this guy right here. Okay, so for instance then, what this says is iron could be +2 or +3. It doesn't follow this rule. Well, let's read our rules. So for metals that commonly have only one form of the stable ion, the name of the ion is simply the name of the element from which the ion was formed. So that's why earlier today, you guys told me the formula for table salt was NaCl. What's the name of that? It is sodium chloride. I'm gonna, sometimes when you're learning new things, if you go back to what you already know, sodium chloride, NaCl, what does that look like? Why is it like that? Why is there just one sodium and one chloride? So the name of sodium chloride is simply sodium because it forms only one cation form. So it looks like this. So this here in this last bit is what, and I call can you hang your hat on? What can you always say it's always going to form that charge? Oh no. So just a little bit ago you took your periodic tables. And over 1A, you put +1, right? Over 2A, you put +2. beginning with aluminum, you put +3. Only one choice. Notice that germanium, tin, and lead, you didn't put, what would that be? You didn't put +4. And the reason for that is we don't know what way they're gonna go. You have to just assume that these are question marks with regard to what sort of cation they'll form. Actually, then they're picking up electrons, so that would be, yeah, picking up electrons. So you don't know these, you don't know these, and you don't know these. Iron's one of these. Now, I told you there were 3, they're kind of hidden in here. There are 3 in here that you already know, and they're on that slide, and they're next to each other. Zinc and cadmium are always +2, and silver is always +1. Okay, so just to kind of recap, just like you call table salt sodium chloride, if something is in 1A like sodium, the first name of that ionic compound is just going to be the name metal. Just the name of the metal, just the name of the metal, just the name of the metal, okay? For everything else, then, what do? Well, you have a couple of options, okay? So for metals like iron that form more than one type of cation, and I told you that you're gonna have to assume it forms more than one type of cation if, that's why you broken record sometimes, if your metal is not here, if it's not here, it's like a chicken. If your metal is not here, and if your metal isn't this, then you're gonna have to assume it forms more than one sort of cation. And so you can go a couple of different ways. My favorite way is just simply to use Roman numerals to say what the charge is. Now I've started doing this because not everybody knows your Roman numerals. Let's see how good we are. So what's the Roman numeral for 1?
I.
I, very good. Perfect. So the number 1. Okay, so the Roman numeral for 1 is I. How about 2? 2 I's. 3?
3 eyes.
4?
IV.
It is IV, yep. Because like it's 5 minus 1, which is 4. How about 5?
B.
Perfect. 6?
VI.
VI. 7?
2 eyes.
VII. 8? 3 I's. 9? IX. Very good. 10? X. So that's the Roman numerals we put in parentheses. So, for instance, if we have an Fe +3, the name is going to be Iron Man. The name is going to be Iron Roman numeral 3. That's all. That's it. I think we have another go around the room. This is a figure from this slide I feel is redundant because it just has to be. So just to repeat, make sure we're all on the same page. Now, on your Unit 4 exam, you're going to be faced with naming compounds. And if you use Roman numerals for metals, and you're not supposed to, you get it wrong. They're only worth 1 point apiece. And if you don't use Roman numerals when you're supposed to, you get it wrong. Okay? So let's see how we did. So who do we last leave with?
This is probably
It's ready for Tristan? Okay, Tristan, what do you think? Is it calcium 2 or is it just calcium? So use a periodic table, find it on the periodic table. And if you have a thing marked at the top, then it's just calcium. It's just calcium. Yep, just calcium. If it's in a compound, it's just calcium. Find it on the periodic table, Lindsay. How about K plus 1? Just potassium. I can never spell potassium. Sierra, what about barium? It's just barium. And if you're like me, you think you kind of know the periodic table, but sometimes it's like you have to find it because it's not where you might think it is. So find it on the periodic table. What do you think, Jacob? Do we use Roman numerals? In this case, it would be what?
two, what do you think?
So these are original